All right. Hopefully you all had a good weekend. Uh, just as a reminder, we have an exam Wednesday. So we'll take that exam in here. You will be allowed to bring in your calculator, something to write with, and your equation sheet. Any other electronic device that you have on you, I will consider that not allowed, and I will take your exam if you have something else out. All right. And that includes like a watch or a phone or anything else. You're not allowed to have other electronics out. Is everyone good with that? All right. So if I see that, then I have to take your exam from you at that. Also, just so you know, I will require you to have space between each other, right? So no one's going to sit next to somebody else. Because we have plenty enough room to spread out in this class. Any questions about that? No? All right. So your exam will be 15 multiple choice and 3 extended response. The extended response, there will be that sheet that it says, what were you given? What are you looking for? What equation should you use and then solve? You'll have 3 copies of that, one for each extended response, so you can work out your answers on that. That's attached to the exam. The multiple choice, you'll fill in a bubble sheet for that part. Okay? Is everyone good with that part? Any questions on that? Also, as a side note, your equation sheet needs to be handwritten unless you come to me for some reason and say, I cannot handwrite this equation sheet. It has happened a few times in the past. Somebody broke their hand. So they broke their writing hand. They couldn't write. But other than that, I'm assuming most people can write. But if you forget your sheet, I will print the one that's online. That way you can have a copy. Like if you forget it, your equation sheet. Any questions? All right. Tonight I'll meet in here at 6 o'clock. So if you can come tonight, I'll be here to answer any questions you have. At 6 o'clock, it'll also be on Zoom, and I'll record it and post the video to our video recording spot on Canvas, which is a tab in the modules. That's where I've been putting all of our videos. Also, there's some they're called extra questions in learning catalytics. Those are just extra practice questions you can do. You can do it outside of class. It's just open there for you to look at some extra different kinds of questions. Any questions? Does anybody have a question in general they want to ask? Yeah.
Do we have to write the equation sheets before the test?
No, yeah,
before we take the test, or can we have that already?
You should have it ready when you walk in, right? It should, when you sit down to take that exam, you're ready to go. Good question. Anything else? It can be like, 1D motion, 2D motion, vector, like you can have a category heading. But if you start really trying to really sub-label it too much, then that can be a little bit. But you can have broad categories to help organize your sheet into regions. But no pictures and no explanation. All right. So I'm just going to kind of go through these again with a little more detail than we did the other day when I just kind of glanced over them. So one of the things you should be able to do is interpret motion diagrams and graphs to represent motion. And so when we're talking about graphs, we've started with something like this. We had some kind of position time graph. And the first one we looked at was something kind of like this, right? That look familiar? And then one of the first things we kind of noticed about a position versus time graph is, what does the slope of this graph represent? The slope of this graph represents its velocity, right? Then we did look at, we had these lines, and depending on the steepness of the slope, that meant that the bigger the velocity. So if you have steeper slope, larger velocity. Now we did also eventually add in a couple different position versus time graphs. We said that, hey, you could get something that looks like this. We also had something that looked like that. You could get something that looks like this. And you can also get something that looks like that. So there's 4 of these ways these curves can be on a position versus time graph. And what is a curved XT graph tell us when we see that curvature? What? Acceleration. That means we have an acceleration, because what that's telling us is the spacing of the dots and the position and the change in position is growing or shrinking with time. The spacing isn't consistent, right? So that's what we remember, that the slope of the position versus time graph is velocity, and curvature means acceleration because the velocity is changing. Now, how do we find displacement on a position versus time graph? Yeah. No? Well, so if I give you any 2 points and say, how do we find the displacement? What do you do? Yeah, let's not overthink this. So if you're given position versus time graph, you just take the difference between 2 points, right? Hey, what's the displacement from this time to this time? Just take the 2 points. Please don't overthink this one. All right, that's all I'm trying to say. Is like a lot of times I've seen that. Like I'll ask a simple question, thinking, "Oh, this is a gimme," and like everyone gives me some strange. So I just want it to be nice and straightforward. All right, so this is position versus time. What we get now. Then we looked at we looked at velocity versus time, and the first one we kind of looked at was something like this. And so what is the slope of a velocity versus time graph? Yep. This represents the acceleration. Now, when we were looking at accelerations, there was actually 4 different ways we could have an acceleration. So there was this one. We also had this one, and then I'll draw the last one just so they're not, I should have made room on this one and this one. So these are 4 different velocity slopes that we can have, and they represent different things. We're going to come back and talk about that in a second. But there was 4 different slopes of velocity versus time graphs, right? 2 positives, 2 negatives. Now, what the last thing is what can we, what does the area of velocity versus time give us? What? Someone say it. Displacement. So the area in DT graphs gives displacement. So these, we should be able to interpret graphs and explain something about the object's motion by looking at a graph. Is everyone good with that? Now, the other one that's in there is that motion diagram, and that's the one where they give you the dots, and you're like, oh, it's speeding up because the dot spacing is growing. It's slowing down. The dot space is getting smaller. It's staying at a constant speed. The dot spacing is the same. And those questions were probably in your the dynamic module and in the concept question, where you had all the little dots. All right, so this is our graph motion, interpreting. So the next one is calculating the speed, or velocity of an object. How do we do that? What's the equation? One of the first equations we got. Yep. So V is delta X over delta T. Right? That's our first basic thing there. And the speed we're going to say is magnitude, right? Depending on what information they give, can also be distance. So scientific notation, is everyone good with that? That's where you have the one number, the decimal, any other digits, and a power of 10. Does everyone remember that? Okay. So then we need to be able to express quantities in the appropriate units and have the correct number of sig figs. So this would be, you're given two numbers to add, you have to get the sig figs right, or you're given two numbers to multiply and you have to get the sig figs right. We're good with those two rules? Okay. Perform a unit conversion. So you all can do a unit, everyone here can do unit conversion. I hope. Yeah, make use the picket fence if you have to. You're allowed to write unit conversions on your sheet. So if you want to put some on there, you can. Second thing is, if you need a unit conversion and you don't have it, you are allowed to ask. Most of the time, I will provide the unit conversion if they're different, right? So like if you look at the extra questions I gave you, there was one with like hogsheads and rods. I will tell you whatever those conversions are because they're not standard, right? But you know, for the most part, you should know like 1,000 meters in a kilometer, those kinds. But if you need to write them on your sheet, that's fine too. All right. Or if you need me to give you one, I will do that. Is everyone okay with that? I'm expecting you to be able to do the math part of it, not memorize unit conversions. That's what it is. Now, there is one unit conversion I do want to spend 1 second talking about. And it's not necessarily a unit conversion, but it's part of unit conversion. So if you're given 100 square centimeters and they ask you how many square meters is this, a lot of times what I see is people will say, I can do this. And then they tell me that this is equal to 1 meter squared. So they tell me that 100 square centimeters is equal to 1 meter squared, but that is wrong. All right, here's why. Let's think about what this would mean. So if I had just, I'm not going to draw this all out, but you can imagine that I have 100 little cubes because I have 100 divisions on a meter stick that are a centimeter long. And then if each one was 1 centimeter wide, I'd have 100. But 1 meter squared is also going this way 100 times and breaking it into 100 cubes this way. So when you're done filling in this area with cubes, if you have 1 meter this way and 1 meter this way, that's 10,000 cubic centimeters. Because you have 10,000 of these little cubes that are 1 centimeter by 1 centimeter in this area. The key to remember is whenever you have a power, that is the number of times you apply the unit conversion. And so if you have 100 centimeters squared, you have to apply this twice, and then you would get 0.01 meters squared. Is everyone good with that? So whenever you have a power in a unit conversion, you apply the conversion that many times. Because centimeter squared is really a centimeter times a centimeter. So you have to apply the conversion twice to get rid of that centimeter squared. And that's one just a lot of people forget. We'll see this again when we talk about volumes later on. But it's important because a lot of times, right around now, they're dealing with areas and things like that. Is everyone good with that? Okay. Motion vectors. So this is just being able to break your velocity vector into components. And then like with the trig stuff, that's like I said, that's going to be more about projectile motion stuff. But breaking your vectors into the components is what I really care about out of that. Okay, velocity shows up in 2 chapters, so it gets an outcome twice. All right. So the other thing we're going to do, and then we'll come back to the bold in a minute, is calculate the acceleration of an object. How do we calculate the acceleration of an object? Huh? Yeah, what's the equation we can use? The basic equation that we can use to find the acceleration. Acceleration, delta V, delta T, right? So you should be able to do that. Be able to calculate acceleration. Now, here's where we're gonna change up the gear a little bit with these graphs. And then I'll pull this back down. So we said that when you're accelerating, the acceleration is, you also have to look at the velocity to get the acceleration sign correctly, right? Those two are interplayed. So there's four combinations, we said. You can have a positive velocity, positive acceleration. This means you're speeding up, right? If you have a positive velocity and a negative acceleration, you slow down. If you have a negative velocity, positive acceleration, this is also a slowdown. And then if you have a negative velocity, negative acceleration, you're speeding up. So these are our four combinations. And you can think of this one as kind of like velocity initial, your starting velocity. Is everyone okay with that? Does that sound familiar? All right, now when we're thinking about, I'm going to cover this up for just a second. So when we're thinking about our graphs, this is positive V, positive A. This is something that's speeding up. This one here is negative V, negative A. This is a speed up. And this is a speed up. Now this is positive V, negative A, negative V, positive A. These are your slowdowns. And the way that you can also remember this visually, if you need to remember this, if this line tends towards V equals 0 to this line, notice this line is moving into V equals 0 on both of those. That means you're slowing down. And the speed ups, you're moving away from V equals 0, right? So you can think about those lines that way. These two move towards 0. This one's moving away from 0. This is a speed up, speed up. You're moving away from V equals 0. That's how we can tell we're speeding up. Is everyone good with that? So that's why we have four combinations. Yeah, cool. So then you should be able to do that if I ask. All right. So then we have these other things here as well. It says solve problems about an object in uniform motion. And that could be either as a quick calculation using like one of those two equations, or it could be some kind of long answer. And then we also have the problem solving approach for problems with constant acceleration and free fall. So the uniform motion means like your A is constant and different. That could be one of those A is one here, A is something else here. And then we also have free fall. And so there was something about free fall. There was two special conditions I want us to remember for free fall. What were those two conditions that we had for free fall that they're not going to tell us? Well, actually, I'm going to write it a little bit over more. I know it's tough to see right in here. So what are our two special conditions for free fall? Yes, so AY is G, which is our 9.8 meters per second squared down. That's one. What's the second? That's only if it's symmetric, right? We ignore air resistance. All right, you ready? What's the special point? Yeah. Vy top is 0. This is at y max. And yes, if we have symmetry, we're going to talk about that in a second. If you go back to the place you started, then the time up is time down for symmetry. And the velocity is the same at launch as it is coming back to that same point, right? But this is our general one that we can just stick with. All right. But yeah, all those points were good, but this is the two I was kind of like, make sure you have that on your sheet. It's important. Is everyone okay then with free fall? Okay. So the other couple things that I'm going to finish up writing on this board here, add and subtract vectors graphically. This isn't talking about you needing the protractor and ruler that you couldn't bring those. I guess if you really wanted to, you could, and I wouldn't stop you from using them. But what I'm talking about more is like if I give you two different vectors, and these are both the same length, then I say, this is vector A and this is vector B. Like if you add them up, you would get 0, right? Or if I said, hey, you're given this vector and this vector. This is A and B or something, and they're the same length. If you add them up, you should get something like 2A, right? So I'll give you a list of options, and then you just have to pick which one is correct. All right, but this is generally what I'm talking about with adding and subtracting vectors graphically. They're going to be the same length. They'll just be oriented, and then you have to pick the combination that looks correct. Is everyone good with that? And I think you had some homework or concept questions like that. So that'll be what it is. Yeah, you won't be expected to have. I mean, you actually can solve problems with the protractor. If you're fast, knock it out pretty quick. So vectors and motion diagrams to find acceleration. So we've talked a little bit about motion diagrams, but what we're also thinking about is projectile, right? And so when we have a projectile, we have to remember that we launch at some angle V or some VI at some angle theta. So we really need to remember there's a VIY and VIX. And in our projectile, we then remember that at Vy at the top is 0. This is at Y max. But when we're going up, we remember that Y changes, X does not, because AY is G down, AX is 0, right? And if we land at the same height, if we start and stop at the same height, then we have our symmetry. Time up is time down. VI starts this way, it'll end in the opposite direction because it'll flip directions because VY shrinks, goes to 0, and then speeds back up. AX is constant. Is everyone good with that? And then we just remember, what is the acceleration all the time when something is in the air? Yes, don't forget that. It's you got to remember that, right? And don't let me trick you. I'll try. I'll give my best effort. Make sure you're really confident in what you're doing. But don't let me trick you. Just remember this. Hold true to that. Whenever there's a projectile. So remember, this is solving two one-dimensional problems. One in the X, one in the Y. The one in the Y is free fall. The one in the X is just one, it collapses to that one equation. Is everyone good with that? All right, so then let's put down some equations. And then we'll talk, oh, I gotta do that one part first, then I'll come back and do that one. So then we had our three equations. We had V final is V initial plus AT. We had V final squared is V initial squared plus 2A delta X. And then we had delta X is equal to VIT plus 1/2 AT squared. And that was kind of our general set. Then we had the one specialized set for the y motion. And that was v final y is v initial y minus gt. V final y squared is v initial y squared minus 2g delta y. And then we had delta y is equal to viy t minus 1/2 g t squared. So these were the equations we used for free fall in the y part, right? Then if we throw in an angle, we get to recover this one special equation, delta x is vit, right? Is everyone good with that? All right, so then we should be able to solve for projectiles that follow parabolic trajectories. And I said symmetric and non-symmetric. So symmetric is when you start and stop at the same height. Non-symmetric is if you're like going out of a window or off of a cliff or something at some angle. That's a non-symmetric. Is everyone good with that? And I did post a video about somebody throwing like a baseball off of a cliff or something, which is a non-symmetric, so you can see how. But all of these problems, I always say use the same strategy: find time up, find y max, find time down, right? And then you can do those couple steps. It's 3 steps, but you can do them all the time on any problem, whether it's a free fall or a parabolic or a projectile. Those steps are the easiest 3 to do, and then you can crack any other problem. Is everyone good with that? All right, then the last thing I wanted to do is perform vector calculations. I'll just write that up over here real quick. So whenever we have vectors, the generalized solution is if you have, let's say, you need to find r, and this is a plus b plus c, then what we do is we take each one of these vectors and we break them into components. Ax is a cosine theta. Ay, a sine theta. Bx is b cosine theta. By is b sine theta. And then cx is c cosine theta. And cy is c sine theta. And we do that because we remember that we can build a new triangle R off of these 3 vectors, so that AX plus BX plus CX is RX, and RY, the new Y component of the new vector, is AY plus BY plus CY. Then we know that the length, using the Pythagorean theorem of our new triangle, is just ry squared plus rx squared square root. Then finally, the new theta resulting angle is just the tangent inverse of ry over rx. That all sounds familiar? Okay. Then of course the other part is if you have a minus b, when you see this, it's just a plus the negative b. So you, in this case, add 180 degrees to the angle. And then all else follows the same. The magnitude doesn't change. You just add 180 to the angle and then stick it in. And that'll give you the correct. Right? So try not to, so the 2 solutions are just trust the angles that are given and plug them directly in, or you sketch up the picture and add the plus and minuses accordingly. I always recommend just stick with the sines and cosines and let that dictate the plus and minus. It eliminates you making an extra angle, like doubling up a negative. Okay? And you should be able to do that as well, according to this. Now there's somebody asked this before. I forgot to mention the first section, but you get this information because I remember the second section. Circular motion, the circular velocity things are not on there. Neither is random It's not on this sheet. It's not on the exam. All right. So that's usually how I do it. If it's on these sheets, then it's fair game on the exam. I know you had some homework and stuff on it, but don't worry. You'll see it in chapter 6. So I don't want you to think, it's not going to come back. It'll be there for chapter 6 when we talk about circular. But these are what you'll be tested on these things. Right? Is everyone good with that? Does this raise any other questions that you want to ask? All right. So what I have for you then, I have some other problems for you to work on. These are just for you to work on. I'm not going to collect these. There's nothing. They're just extra problems to work on. I'll post the solution at 1 o'clock. So take one, pass it along. Next lesson is work with your neighbors, talk to other people. If you have questions, you can ask me. Make sure. You want me to check it? Until we get wild. The other one. Does everyone have one? On Zoom, worksheets will go up in just a little bit. You'll have access.